Okay, can everyone hear me? Mm, Not getting audio. Yep. Okay. So we're going to get started today. Today we're going to be talking about kind of some best practices for installations, things that we found work out better, and a lot of things we've learned from field installations of just things people have done incorrectly, which have caused problems, and how to avoid those. We're going to talk about some of the system design and stuff that we do before we go out into the field. The physical installation, where we put the inverters and the batteries and how we mount them, and then some of the electrical installation, what kind of wires to use, some details there, and talk a little bit about surge protection. Talking about whole house backup. A lot of people want to do whole house backup, but it's not really what this inverter is best intended for. It's got a built-in 100 amp transfer switch, and what it's really intended for is to back up a 100 amp backed up loads panel. The inverter only has 47.5 amps continuous output, 42 amps continuous output on battery only at nighttime. So backing up a whole 200 amp house with a 40 some amp inverter, not a real good match. Recommended that you do a separate backed up panel and use the extra smart load outputs for less important backed up loads on separate sub panels. And then you can kind of segregate your loads and kind of pick which ones are more important, which ones turn off sooner. One thing that seems to be missing on a lot of installations nowadays is doing a load analysis of the backed up loads. 30 years ago, whenever we were designing an off-grid system, we would always calculate what our peak continuous load, our peak surge load, how many kilowatt hours load we expected over the day, how much percentage of that was at nighttime operating off the batteries, how much might occur during the daytime, and prioritizing the loads. Like, can we put more of our heavy loads in the daytime, in the afternoon when our batteries are full and we have extra solar, versus running them at nighttime when we're pulling our batteries down more. It can be difficult to get all this information, and the tendency I see a lot is to say, I've got 2,000 square foot house. Is one inverter enough? Yeah, you might as well ask what color is the trim around the windows. It's almost as relevant as the square footage of the house. I've seen 600 square foot house that was way too heavy at loads for one inverter and one or two batteries. And I've seen a 3,000 square foot house that one inverter and two batteries would provide a very nice backup power system. It really depends on what kind of loads are in there and what kind of pattern of operation you have. So to the extent that you can, trying to get more information on what the loads are will really help you design a better system. All the old catalogs used to have pages of tables that you filled out and did this load analysis. Now that we've kind of gone to the internet and no more printed catalogs, it seems like a lot of people have kind of forgotten this part of the design step. But it's still important, and I still recommend doing that, because we see a lot of systems that aren't performing real well. And when we get into it, we see that, well, you've got two batteries, but you've got such heavy loads that you're starting the generator twice a day because it can't even make it through till morning on those two batteries. It's got such heavy loads. Or it just doesn't have enough solar and you're running the generator in the summertime. Wintertime, you kind of expect to have to run the generator, but in summertime, with the price of PV nowadays, you really shouldn't be running a generator when you've got good solar resource. So thinking some about the load analysis and how that affects your system design rather than just kind of using rules of thumb like this size house is one inverter and 8 kilowatts of solar. That's not a real accurate way of doing it. Now, getting back to whole house backup, one question. The Emporia power monitors, I actually like those quite a bit for when you have an existing house and you're thinking about what to back up and seeing how much does the refrigerator draw versus the electric car charger and things when you're trying to think of what to put on backup power. It can really give you as a designer an idea of what in the house is currently using loads and what really shouldn't be on backup power and what wouldn't be a problem at all. It also can show the customer, because a lot of customers don't have a real good idea of what uses a lot of power and what doesn't. Some are thinking, well, I don't want to back up the TV and the computer because those draw a lot of power, but I want my electric heaters to run if the power goes out. Those actually draw way more energy than the TV and the computer, but it can be hard to convince a lot of customers that unless you've got some data to show them that. So I do really like some of these cheap power monitors. The Emporia is one of the better ones, I feel like. It's good enough to be pretty accurate, but still not into the like $1,000 plus range of like the more commercial data loggers. On whole house backup, sometimes that's what we end up doing. Just because it's an existing wiring, we can't manage to break out backed up loads separately just because we'd be doing so much drywall work, redoing wires halfway across the house to do something like that. So there's a lot of cases where, despite it not being the best system, we end up doing whole house backup for 200 amp service. One way of doing this is 2 inverters, and then you have essentially a 200 amp transfer switch built into the inverters to do the whole house backup. But you can do this with a single inverter with an external transfer switch. There's some of the external automatic transfer switches that don't rely on a specific generator. They just sense grid loss and switch to the backup source, which would be the output of the inverter. A lot of the generator transfer switches rely on the generator for the kind of the brains of it, but there's some, the Kohler RDT series, I believe, but you'd want to look into the exact ones and make sure. But there's some of them that can work within an inverter to basically switch the whole 200 amp service over to the inverter output if the grid fails. The AC in to the inverter has to be pulled off of the grid side of that transfer switch, not the load output. Otherwise, when it switches over, it's going to be feeding itself and it gets really confused. There's a lot of drawbacks to doing this. One is that if you have a heavily loaded 200 amp panel and its load is greater than the inverter output at the moment it switches over, your inverter will instantly shut off from an overload. It's not very useful. If you know that the 200 amp load panel on the house is not really heavily loaded and it will be fine on one inverter, you can do it. But then the issue is the customer doesn't know when the grid goes down. So a lot of them will say, I'll just manually shed my heavy loads if the grid goes down. So I'll turn off the air conditioner and the jacuzzi if the grid goes down. But if you got whole house backup, they don't know that the grid went down. I mean, yeah, they can go look at the lights on the inverter or pull up their app, but they don't get like a notification like, oh, all of a sudden the lights all went out. The grid must have gone down. So if you've got a critical or backed up loads panel, try not to call it a critical loads panel because that is something completely different in the code. And trust me, you do not want to be subject to those code requirements. So we try to use the term backed up loads panel instead. But if you've got a backed up loads panel, you can kind of get rid of those big loads. But when the customer has the whole house backed up, they don't know that the grid even went off to know to turn off those loads. I've also had the situation where the solar system actually handled everything so well that they didn't know the grid went off for almost a week. And the utility didn't know because this customer was on their own feeder through the woods, and they were relying on the customer calling to say, hey, my grid power is down. So it took a week for the customer to realize they had been operating completely off grid and to call the utility to come repair the power line. With really heavy loads, if they're running at the time that the grid goes down, the customer can't even manually shed them fast enough, even if they know the grid goes down. So if you're pulling, say, 85 amps from the grid and it goes down and that transfer switch clicks over, unless that customer's standing there right with his hand ready to flip off that breaker to the heavy load, can't get it fast enough to prevent overload. And also, when you're using an external mechanical transfer switch, there's always a little blip, at least a second or two, when it switches over, because it's got to notice the grid went down and then switch. And they're usually designed to wait for a generator to come up to speed. Often those are waiting, say, 10 seconds. But even if you set them on the minimum, you're going to have a half a second to 1 second power blip when it changes, resets all the clocks, shuts the router off, things like that. If you run through the integrated transfer switch that's inside the inverter, it's fast enough that you don't have those blips that knock all the computers and everything offline. So that's a disadvantage of using an external transfer switch. And of course, it drains the batteries quickly with non-important loads, versus having them on smart loads where you can set, if the batteries are full and it's a short outage, or if the sun's out, keep running the, I don't know, some big heavy load, or in a less important part of the house. But as soon as the batteries drop to 80%, dump some of those and keep that power for more important stuff. You can do that when you've got it wired in on backed up loads panels using the smart load breakers, but not so much when you're just backing the entire house up. So, like I said, I realize a lot of times you end up backing the whole house up just because of the way existing wiring is. I've ended up doing it, but it's really not the best, and it's got some drawbacks. One thing we want to think about is, even though our inverter it's still recommended that we have an external bypass switch, just in case we're servicing the system, we're doing work on it, maybe we've got to swap a battery out, whatever, that you still can get grid power through to your backed up loads. That could be a separate manual transfer switch, just a on-off knife type blade type switch. That could be an auto transfer switch, kind of set up in the opposite direction as we were just talking about, where it normally feeds inverter power through to your backed up loads and automatically switches to the grid power if for some reason it loses inverter power. You want to make sure that it doesn't connect the two together, because that will confuse and possibly damage the inverter. Most of those are designed to not do that, because you don't want to do that with the grid and a generator either. You want to verify that. Another way to do this is on your backed up loads panel, put a generator interlock where you've got a main breaker and then a back-fed side breaker. And one of those is fed by the inverter output, and one's fed by another feed off of the grid panel. And they've got a little mechanical interlock, so both of them can't be on at the same time. That way you can, if you're servicing the inverter, you can flip that interlock and still feed your backed up loads from the grid. Now, don't do a generator interlock setup like that on the main panel that has a sub breaker feeding the inverter. I've seen people do that, and what that ends up doing, it just doesn't work very well for many reasons. But one of the things that can happen is you can end up with the inverter output feeding back around into its own AC input. Then it thinks, oh, the grid came back, I don't need to be doing output. But then when it turns its output off, the grid stops, so it ends up all confused because it's feeding itself. So make sure that you don't have that kind of situation if you're using a transfer switch. Another thing to think about on system design is your PV array design. We've got a 30 amp operating limit on the first MPPT and 22 amps on second and third ones. This translates into roughly 40 amps for maximum current, which is defined in the code as 1.25 times ISC of the PV array, and on 2 and 3, a 30 amp. Remember to include bifacial effects when you're thinking about this. If you're doing bifacial ground mounted arrays, they could be somewhere in the 10 to 25% higher current than the normal SDC rating. We don't want to exceed this current because that's going to cause damage to the inverter. We also want to make sure that we never exceed the 600 volt upper limit. And remember, this is at record low temperature, not at STC conditions. So you've got to do the math and calculate what is the actual open circuit voltage of the array on that cold winter day. Typically 15 to 25% higher. In more moderate climates, it might only be maybe 10% higher. And also older modules had a higher temperature coefficient, so they'd actually climb more in cold weather than a lot of the newer modules, which are a little more temperature stable. But still, where I'm working, usually I'm around minus 30 centigrade for our winter low temperature. And that's a 16 to 20% increase in voltage. So keep that in mind when calculating lengths of strings for staying below that 600 volt upper limit. Now, it doesn't matter if you're at 580, but you don't want to be above the 600. And that's just a voltage rating of all the capacitors and transistors in there. The lower limit, we've got a 90 volt lower limit, but you will see reduced performance under around 120 to 130 volts input. So while it can go lower, I would generally try not to. The efficiency of the MPPTs drops there. And also, because you have that kind of a strict amperage limit, you just can't get very much wattage out of a low voltage array without hitting your amperage limit. So say you had a 100 volt array, 30 amps operating, that's only 3 kilowatts. Whereas that same input, if you had several hundred volts coming in, you could be 6-7 kilowatts on that same one input easily. So you really limit your wattage input by having a lower voltage array because it's the same amperage limit regardless of the voltage. This really comes into play when you're reusing old PV arrays that used to be on a 150 volt charge controller, and now you're revamping the system and putting an all-in-one in. Often we need to reconfigure the strings to be higher voltage and lower amperage. I usually do this in the combiner box, basically, instead of using that paralleling comb to parallel all my old strings, I'll use Polaris connectors or something equivalent to series sets of maybe 2 or 3 of the old strings and then parallel those to give myself a higher voltage, lower amperage array without having to get up on the roof or up on the back of the ground mount and reconfigure the actual wiring on the PV array. I reconfigure it in the combiner box. Also, check for any grounding of the old array, intentional or inadvertent, because the all-in-one really needs an ungrounded system, and it's floating on both the positive and negative, and if either of those is grounded, especially from old ground faults that were unnoticed, the old systems really couldn't see negative ground faults, then bad things can happen. So you really want to check to make sure the array is floating before you connect it to the new all-in-one if it was an old array off of a old style charge controller. On the string sizing tool, we don't have a string sizing tool, but that's actually something I could put together pretty quick. Basically be an Excel spreadsheet that you can put in the characteristics of your panel and it'll spit out string sizing for you. So I'll try to do that and I'll email it out to the list. PV array disconnects. Obviously, we've got the one built onto the side of the inverter, but often you want an external one where the PV circuits enter the building. Especially if you've got a remote ground mount, you might want to have a disconnect at the ground mount before it goes underground, a couple hundred feet to the house. So one thing to be aware of is that the PV array disconnects need to disconnect both the positive and the negative poles of the array. And that's because this is an ungrounded floating array. It's actually a lot more sensitive to detecting ground faults if you haven't grounded one of your conductors already. And that's why virtually all of the high voltage string inverters went to that 10 plus years ago. But it's been relatively recent, really only with the proliferation of the 600 volt charge controllers and the all-in-one inverters, that we really have run into these ungrounded arrays a lot on battery-based systems. So it's something new that may not be in your kind of thought process when doing battery-based systems. There's kind of 2 options for these external disconnects that disconnect both poles. If it's just one string, you can use 2 poles of the old 600 volt square D knife blade type switch. But there are some newer and cheaper options, especially to do more than just 2 poles at once. Because say you've got several strings. One of these are the IMO. There's a bunch of different distributors carrying the IMO disconnects. They work fine. They look a lot like the little twist switch that was on the bottom of the old SMA string inverters, possibly exactly the same internally. I don't like that they're in a plastic box most of the time. And if you've mounted that on, say, the exterior of a house, I just question long-term holding up to UV. But they work good. The thing I prefer is using the MidNite Solar disconnect box. It's got the little red handle on the cover that operates the breakers. And using the new 600 volt 2-pole breakers, you can separate the 2 poles and use one for the negative and one for the positive. Both poles have to be in series to get the 600 volt rating, but using one on the negative and one on the positive of the same string, they're still in series. It doesn't matter if they're directly in series right next to each other, or if one is on the negative and one's on the positive. So that way you can get 3 of those breakers in one disconnect and disconnect 3 strings all at once. And for troubleshooting, you can measure each string individually and turn on and off each string individually if you open the cover. So that's kind of nice versus the IMO where you can't turn on and off individual strings for troubleshooting. A nice thing about having a disconnect, especially these the MidNite solar ones that can take larger wire, is if you've got larger cable coming back from a remote ground mount that's bigger than 8 gauge, is 8 gauge is the largest you can put into the terminals actually on the all-in-one inverter. You can use that disconnect to transition from that large cable coming back to some 10 gauge or 8 gauge for the last little jump into the building and over to the all-in-one inverter. Physical installation. We want to think about clearance around our inverters and batteries. Obviously, we've got code clearance of needing 3 foot in front of them for access and proper height of the location. We also want to think about ventilation, especially of the inverter. Batteries, ventilation is less of a concern, but the inverter, it's putting off a bunch of heat when it's operating. It's pulling in air from kind of behind the wiring compartment, and it needs 6 inches on the sides to be able to pull that air in. And then it needs 6 inches above the inverter, preferably a little more, but minimum 6, to let that hot air out. If you've got a whole bank of inverters, say you're doing a multi-stack, you're going to be putting off more heat, so maybe a little more room would be better. For batteries, we want 12 inches between the batteries, and that's per the UL 9540A fire testing, so that if something happens to one of the batteries, it can't spread to any other batteries. So some of the cabinets and stuff which we're working on will give us a little reduced spacing there, because it's not just free air between those. We're going to have separators and things. But if you're just mounting them on the wall, you're going to have to do that 12 inches. Some jurisdictions are sticking to 36 inches between each battery, which is kind of the default in the NFPA 855 battery code. If you don't have the fire testing, it is supposed to be overridden by the manufacturer's results of the fire testing, which says 12 inches in our manual, but not all jurisdictions are accepting that. LA Fire Department is one I've heard is not doing that. So you may have to have more clearance for reasons like that. We want it to be mounted on a non-combustible surface, drywall, concrete, or a layer of concrete board or tile backer over wood qualifies there. And obviously it has to be able to support the weight of the equipment. The inverter's a little over 100 pounds, the batteries are almost 300 pounds. You need a nice sturdy wall, and like just some drywall anchors isn't going to cut it. Mounting to 2x4s or 2x6s in the wall, probably good. If you're mounting batteries in 2 rows with an upper and a lower row, the batteries are not supposed to be solely supported by the wall mount to meet their seismic resistance. You can just hang them on there, but they're not going to be seismically rated if you do that. So you want to have a support underneath. What I use is a piece of like 3-inch angle iron bolted solidly to the wall that battery can kind of rest on for some of the weight if I need to get the seismic resistance on a row that's not sitting on the floor. Physical installation, continuing, we want to think, what kind of environment are we putting them in? The PowerFlow 16 batteries and the inverter, not the rack mount batteries, but the wall mounts and the inverters, are outdoor rated for NEMA 3R. But direct sun's not good. It destroys the displays on them, and it makes them operate much hotter temperature, and that's just not good long term for longevity of electronics. I've seen a lot more failures of even the old string inverters when they were mounted in direct sun than when they weren't, and they were also outdoor rated. It's just the type of thing that is better to, if you have to put them outdoors on a wall, an east or a north facing wall is a lot better than a west or a south facing wall for that reason. And similarly, direct rain, yes, they're outdoor rated. If you've considered fully all the conduits going in and out, are they waterproof? Are they sealed against water coming down cables and following the cables into the equipment? Do you have drip loops? Because you can get a lot of sources of water getting in the equipment other than just from the exterior, and conduits are one of those sources. Even air coming through a conduit from a warm building into a cold exterior cabinet can condense and put a lot of water into the inside of equipment. The PowerFlow 5 batteries, the rack mounts, those are not supposed to be mounted outdoors. In a garage or something, that's fine, in an equipment building, but you can't just stack them up outside. Some of the new cabinets we're working on, or if you have a NEMA 3R rated cabinet, they could go outdoors, but generally they're not something we would put outdoors. Another thing to think about is the wall mount batteries have built-in heaters, and we've seen a lot of people that have kind of taken that idea way past what its intended use was. They're intended for occasional events where we drop below 40 degrees. Say you're in a fairly mild climate where you might get down to 20 degrees a couple times a winter. That's probably fine to do say an outdoor installation on the back wall of the house. Not like in an unheated equipment room in a Montana mountain telecom site where it's 20 below for weeks on end. And we've seen situations like that where it's just not up to doing something like that. It's only a 300-watt heater in each battery, and being an uninsulated cabinet, there's only so much heat that can put in. And also, that's draining heat or draining electricity from the rest of your system. And if you're grid connected, maybe it just is using a little more grid power. But if you're off grid, you got to think, well, so I've got a heater in there, but do I have the electricity to be running that heater all the time to make it function? I see the heaters as good for, like I said, milder climates where most of the time it's 40 degrees and above, and you'll have a cold snap and it might freeze and get down into the 20s, but it's not going to stay there for weeks on end. Also, in a lot of the garage installations in colder climates, it's an insulated garage. It's not a heated garage, and sometimes someone forgets and leaves the garage door open, or you get really cold and it gets down below freezing inside that garage. That's an appropriate use of the heaters for when occasionally it's getting down below freezing in there, or if you had an emergency event like someone forgetting to close the garage door overnight, they could pull off the grid, keep those batteries warm, and you wouldn't have frozen batteries. But when you're looking at consistent cold temperatures, it's really there you're looking into heated equipment rooms with supplemental propane heating, insulated equipment rooms, insulated battery boxes, things like that to really make it make more sense. I got some questions on the heating here. If the batteries are just turned off and stored, so the batteries are actually, the battery BMS is turned off, not just the inverter turned off, because it's still pulling some current then. I believe that would be okay if the batteries are stored at low temperatures. Logan can chime in on that perhaps. The heater, the logic behind the heater is it only turns on if the batteries are trying to charge and they are at low temperature. So at nighttime, it's not going to turn on. And this can be a problem because, I mean, it's got the benefit that it doesn't drain your batteries overnight just trying to keep the batteries warm. But when the sun comes out the next day and it starts to charge, instead of charging, it's just going to put 300 watts into the heater in each battery until it gets that battery back up to temperature to charge. So in some cases, it would be better to keep that battery warmer so it's ready to accept a charge sooner the next morning, rather than often wasting a lot of solar power the next morning because you're just putting a little bit into the heater rather than full power into something. But if you turn it on overnight to keep it warm, you risk draining the battery for no reason if maybe it's still snowy the next day and the power didn't, or the sun didn't come out, and you just keep draining that battery. So we are actually playing around with some different firmwares and revising some of that, possibly even making it selectable which option you want for behavior of the heaters, whether you want them to kind of be more aggressive in preheating the battery to keep it from dropping down, or never draw from the battery and only draw from incoming charging. That is something we're actually working on some improvements on. Installation, using a gutter, also called an electrical trough or electrical wireway, makes wiring to the inverter much easier versus using conduit directly to the inverter. All the knockouts are on the bottom of the inverter, which often ends up with a whole bunch of flex conduit or LBs, things sticking off the bottom for all the different things. You've got DC from your PV, DC from your batteries, AC from a variety of different sources and outputs. Can be a lot of stuff sticking off the bottom of that inverter, and using just one gutter under there can make it look a lot cleaner and a simpler installation. We provide a wiring or a template where you can punch all the holes to match up with the inverter, and just made it right up to the bottom of the inverter. 10-inch gutter mates up very well to the bottom of the inverter and comes just about to the front of the inverter. 8-inch gutter can either be spaced off the wall a little bit with, say, a single piece of strut, or you can use it bolted to the wall and only use the rear line of conduits on the bottom of the inverter instead of both lines. That depends on how much you have coming in and out of the inverter. If you're doing a full thing with grid tie, AC in, AC out in full 100 amp wire, and some AC smart loads, and a lot of PV inputs and your battery, you're going to find that you don't really have enough room only using the rear line of conduits. If you're just doing an off-grid with 1 or 2 MPPTs, your battery input, an AC output that's not full 100 amp because it's only the output of the inverter, and a generator input maybe, it might be pretty reasonable to just use the rear line of conduits. One thing that we've run into quite a few times is drilling additional holes in the inverter or the batteries, don't do this. It'll void the warranty. And the reason is, what happens is little metal shavings get on the circuit boards and short things out. And we've had that happen several times where people drilled holes, a shaving made its way onto the circuit board, and just like you wouldn't take your laptop and drill an extra hole in the side of it, don't drill a hole in the inverter or the batteries. A gutter, that's a piece of electrical equipment. You can drill whatever holes you want in it, do it away from all the rest of the stuff, and then you can put it in there to mount whatever extra things you want. But don't drill extra holes in the actual inverter or batteries. Here's kind of a demonstration of a good use of gutter. This is a 10-inch gutter across the bottom of 3 inverters. And you can see here they've actually used 12-inch wiring boxes to go between the knockouts on the sides of the batteries and then into the bottom of the gutter. So they didn't even have to deal with conduit there. One of these 12-inch boxes has a bus bar for actually combining the 3 batteries and then splitting back into the 3 inverters. And you can see here, when you've got multiple inverters, you end up with splitter and combiner panels to split the grid output into 3 different inverters and then combine that AC output of the inverters back into one combined, in this case, 160 amp feed going back out to the loads. So they've made a really nice clean installation here with what would have been a real mess of conduit with that many pieces of equipment going back and forth otherwise. I probably would have painted the gutters and these wiring boxes here white to match everything, so everything was even more uniform looking, but it's still a really nice clean install. Electrical installation. We see a lot of installs done with undersized cables, and that can cause a lot of poor performance of the system. Battery cables, we want 4/0 fine strand copper cables only. The inverter is pretty sensitive to excessive voltage drop from the batteries. In general, transformerless inverters are more sensitive than the old transformer-based ones, which would just kind of, they wouldn't show you what they were doing. They would sag in voltage during surge loads, and it was pretty ugly looking at it on an oscilloscope sometimes, but they wouldn't shut off. The transformerless ones don't have that big giant block of copper in the transformer to kind of help out with that. So they're more sensitive to voltage drop, and thus we really don't want to undersize the battery cables to them. We've seen them wired with 2/0 and 1/0 battery cables, and that'll work for lighter loads, but pull a full 20 kilowatt surge off this inverter, which is its rated surge, it's not going to be happy when it's trying to pull over 400 amps off too small battery cables. On the AC wiring, the breakers in this inverter are only rated for copper wire. This is a picture of the sticker on the side of one of those 100 amp input breakers, and you can see it says copper wire only. So I know everyone wants to run SER cable to these, but that's not rated for that. Also note that it's only rated for a maximum of 1 gauge wire, so you can't actually get 100 amp rated aluminum wire in there anyway, because that would be 1/0 typically. So yes, you can jam a 1/0 aluminum in that terminal on the breaker, and no, it is not using it according to the listing of either the inverter or the circuit breaker to do that. So copper wire only. 2 gauge is what we recommend for AC in and AC out. 6 gauge for the smart loads and 10 gauge for the smaller smart load. If you're using it off grid and you're not using the AC in, you can size the AC out for the continuous output amperage of the inverter rather than the 100 amp transfer capacity. And that would be 47.5 amps continuous output, which translates to 6-gauge copper wire. If you're grid tied and you're using the full 100 amps, you need 2-gauge. And here's kind of a picture of a wired up inverter. We haven't used all the smart loads in this picture, but see some of the wires coming in and out here. One thing to note is that our PV connectors are behind a bunch of our other wires, as are all of our COM connectors. So best practices are to wire those all up first. That's not what we typically do. We always want to get all the big wires in first and then deal with all our little stuff. But it's really a lot better if we get our smaller wires, our PV array, and all of our COM wires in there first before we start pulling in our 2-gauge and our 4-aught for our big wires and covering those up. Eventually, maybe we can change some of the layout in there, but for right now, order of wiring is do all your small stuff first and then run your big wires in, and it'll be a lot easier. Note that we've got our toroid on the battery cables. You want to get that inside the inverter case as close to the input as possible here. And also we have a toroid here, our DC grounding electrode conductor, which is basically our wire from the ground bus bar in here, either to the ground rod or the U for ground in the foundation, or more commonly in a grid tied situation, back to the AC ground in the main service panel. We want to run that wire around that toroid twice before taking it out of the inverter cabinet. And those help a lot with noise suppression. Another thing on noise suppression is, if you're really concerned about this is for people near ham radio operations or things like that. Using metal conduit, metal cabinets, grounded metal gutters, and making sure everything is grounded is going to have a lot better performance than, say, running SCR cable and PVC conduit between the things, which doesn't give any shielding to that. We want to use a torque screwdriver and a torque wrench for all the connections. And I know most electricians are not used to doing this, but it's specified on all electrical equipment, not just our inverter and batteries. And it is really becoming more important as we start using different kinds of wire and equipment coming from kind of a different background. Like when it was all big knife blade disconnects, they were all pretty much the same from 70 years ago, and they had fairly big beefy terminals designed for standard wire, and everyone kind of got used to that. When we're bringing in some of these newer designs, a lot of the stuff coming out of Europe where fine strand wire is more common, torque isn't always exactly the same as everyone's used to, and there's a lot more potential for over torquing or under torquing different terminals. Also, something we've run into is the battery terminals. Those are brass. They're nickel-plated brass, not steel. So if you crank them down as if you think that's a steel bolt, you'll actually strip that out. So really get yourself an electrical or a torque screwdriver and a torque wrench. They don't have to be these special electrical rated ones, because none of this wiring should be done hot. If you're doing hot wiring on the system, something went wrong in your order of assembling it. You should never be doing that. When you're doing troubleshooting and taking apart old systems and things involving lead acid batteries that you can't just turn off to do the wiring, then you do end up doing hot wiring, and you'll want insulated equipment. But none of the wiring on this inverter should have to be done hot, so you should be able to use a regular torque screwdriver and a regular torque wrench, somewhere $100 or less for each of them, and it's just something to have in your toolkit. And best practice when torquing is to torque it, wait a bit, an hour or two, and then go back and check it again, because some wire types will relax a little bit under pressure, and then you'll need to torque them again. And that's better than just cranking the heck out of them the first time and calling it good. Got some questions on the ground toroid. Yeah, even on off-grid systems, we want that toroid on the ground wire going down to its grounding. If it's grounded to the main service panel, your DC grounding electrode conductor is essentially the same as your AC equipment ground going back to the AC panel, because usually you're just tying your DC ground back to your AC panel. So you'd want that toroid on that AC wire that's coming in with the AC input from the grid. Lightning protection. We do have some surge suppression built into the inverter, so it's better protected than a lot of the inverters out there. However, we still recommend in lightning prone areas, separate lightning arresters on anything coming into the inverter. AC in, AC generator, unless the generator is physically sitting like 5 feet away from the inverter in the same equipment building. AC output to loads, lightning strikes on the house getting into the AC wiring and coming back into the inverter through the loads is a common point of entry into the inverter. Any smart loads, that's also a point where it can get into the inverter. PV arrays, AC coupled or DC coupled, each one needs its lightning protection. And one that people often don't think about is the COM inputs. If you've got a hardwired internet into the dongle for monitoring, if you've got an RS-485 going off to a solar assistant or other monitoring system, you want to have surge suppression on that as well, especially if you've got, say, a remote equipment shed and you're running internet out to it for monitoring. Best practice is to actually run fiber and use little converters on each end rather than copper Cat5 if you're in a lightning prone area. Buried cables are actually just as susceptible, if not more so, than exposed wires, because you get a lot of current in the ground from nearby lightning strikes, which can induce voltages in any buried cables. So some people think that, oh, if I don't have an overhead utility line coming to my house, I'm more protected from lightning. But you might be slightly more protected from a direct strike on those lines, but actually more susceptible to induced currents in buried wires. And you add all this up, this is what? 1, 2, 3, 4, 5, 6, 7, 8, 9, possibly like 10 lightning arresters here, if we've got all these different lines coming in. But that's okay, they're about $100 each. If you've got this much stuff, this is probably a $30,000-$40,000 system. $1,000 to protect that from lightning protection is not that bad in the grand scope of things, and a lot better than trying to do an emergency lightning retrofit because it's gotten fried from lightning. So we always recommend extra lightning protection. If you do take a direct strike to the PV array or to the building, Even the best lightning protectors may not protect you, but I've actually had a lot of situations where I've taken a direct strike and a majority of the equipment with surge protectors on survived, and the stuff without surge protectors on was just blown into bits. Sometimes it doesn't survive, but it's still got a way better chance if it's got good lightning protection. Grounding, we talked a bit about a bunch of this already, but we want to have that toroid on our grounding electrode conductor, whether that's going to the ground rod, UFER, or back to the AC grounding electrode conductor. We want our equipment grounding conductor run with all of our different current carrying wires. This is just standard electrical code. If we're concerned about noise suppression, in addition to the toroids in there, we want to use grounded metal conduit. And we have had some people, ham radio operators, put extra toroids on a lot more wires in there to really get it to the level of noise suppression that they wanted. Best practice, like I said, when doing comm cable, is if we're running Ethernet long distance, is to run fiber with converters on the end. They're under $100 for the converters, and it really prevents that being a source of lightning strikes coming in. For shorter comm cables, using shielded cable, especially if you're running it in the same gutter with all your AC power wires. And for stacked units, the inverters are pretty sensitive to the quality of that stacking cable that goes between the units. We've seen people just using like thermostat wire or something and running it in the gutter along with the AC wires and having a lot of issues, because if those stacked units can't very effectively communicate with each other, they can have a lot of errors, because they really need to know what all the other inverters in that stack are doing at all times to coordinate themselves. So best practice for that is to use shielded comm cable, shielded 4-conductor 18 gauge cable. It's pretty standard security cable, 18 or 22 gauge, and use crimped ferrules on the end of it. It's like $25 for a ferrule crimping tool and a whole package of ferrule ends for that. And you can make high quality comm cables instead of just using whatever random phone cable or thermostat wire you have around to hook up your stacked units, and you'll have a lot fewer errors and things with the stacked units for that. And that's it. If we've got any questions, or Logan, if you've got anything more you want to chime in on. I'm looking through the questions here. People have typed in. Yeah, on these breakers, so it's a common breaker design, but it's essentially in a box that goes up and down, and it's possible, if it's already kind of cranked down, to stick the lug behind that box. Instead of sticking it into the box, you get it underneath the box, and then you end up trying to crank it down farther to pinch the wire instead of pulling it up to clamp the wire. So pay attention to that. It's common with all of these DIN rail breakers that they have that kind of design, and can be hard to see, especially if it's not the most well lit equipment room putting it together, and if the inverter's mounted a little lower. You can always kind of pop the bottom off that DIN rail and tip the breaker up to look at it, and then put it back down, snap it back onto the DIN rail. So it's something to consider when getting those wire connections in there. just the nature of that box can be done incorrectly there. On the ferrules and the communications wire, if you don't have the ferrules on there, you'll find it's pretty difficult to get them in there really securely. When you've got a ferrule crimped on there, you can really just push it and it'll go right in and kind of lock in place. You don't have to be messing around with that little orange release thing at the same time. If you've got just stranded wire trying to put it directly in there, you've got to push the release down to open it up, whereas the ferrule kind of opens it up as it's pushing in. Well, not seeing any more questions. One more thing Logan mentioned is two things with regards to the grounding is anywhere that's very distant from your point of neutral to ground bonding, which is usually in your main AC panel. Your neutral and your ground have the potential of developing voltage between them during lightning strike due to induced voltage. So if you're in a remote subpanel that does not have the neutral and ground bonded, because it's not the main service, you should actually have another lightning protector or surge suppressor in between the neutral and the ground in that subpanel, because they are no longer definitely at the same potential. And also on your battery, we never used to put lightning protection on the 48 volt of the battery because lead acid batteries were a gigantic surge suppressor. You couldn't change their voltage very quickly. Lithium batteries, the actual batteries still perform that way, but we're not connected to the actual battery cells. We are connected through a BMS, which means those battery cells are no longer protecting the DC input of the inverter or the BMS from surges on that DC line between the battery and the inverter. Now, it's usually a really short cable, 5 feet sometimes, maybe 10 feet. But if you're really concerned about lightning in a lightning prone area, putting a DC surge suppressor on that battery 48 volts DC would also be recommended. Okay. Well, not seeing any more questions, I'm going to close it for today. And I'll be working on getting some emails out this week with links to recordings of the previous webinars. And we'll see you next week.